Welcome back to the session on properties of Laplace transform. In this session, first we discuss the property of division by t. If Laplace transform of f of t is equal to f of s, then Laplace transform of the function f of t divided by t is equal to integral from s to infinity f of s ds. That is the properties. The Laplace transform of a function f of t divided by t means just to integrate, we have to integrate f of s, where f of s is the Laplace transform of the numerator function f of t between the limits s and infinity. Consider the function sin 2t. Taking the Laplace transform, we get Laplace transform of sin 2t is 2 by s square plus 2 square. Now we divide the sin 2t by t, we get sin 2t divided by t, and taking the Laplace transform means by this property we have to integrate this function. This is taken as f of s. Here f of t is sin 2t. Therefore, by this property, Laplace transform of sin 2t divided by t is integral from s to infinity f of s ds means 2 divided by s square plus 2 square ds, which is equal to tan inverse s by 2 between the limits s and infinity, which is equal to, on applying the limit, we get tan inverse infinity minus tan inverse s by 2. That is equal to tan inverse infinity means pi by 2 minus tan inverse s by 2. This can be written as cot inverse s by 2 because pi by 2 minus tan inverse theta is cot inverse theta. Therefore, here we can write pi by 2 minus tan inverse s by 2 as cot inverse of s by 2, which is the Laplace transform of sin 2t divided by t. Now consider this function cos at minus cos bt, and we take the Laplace transform of this function means by the linearity property of Laplace transform, we can write this as Laplace transform of cos at minus Laplace transform of cos bt. Which is equal to Laplace transform of cos at is s by s square plus a square minus this is s by s square plus b square. This is the Laplace transform of cos at minus cos bt. Now we want to divide this function by t, and taking the Laplace transform means Laplace transform of cos at minus cos bt all divided by t, which is equal to, from this property we can write this as integral from s to infinity this function. Here f of s is taken as s by s square plus a square minus s by s square plus b square. Therefore, this is equal to integral from s to infinity s by s square plus a square minus s by s square plus b square ds. Integration is with respect to s. In order to integrate these two, we just multiply in the numerator and denominator by 2. Therefore, this is equal to 1 by 2 into integral from s to infinity 2s divided by s square plus a square minus 2s divided by s square plus b square ds. This is equal to 1 by 2 into integral of 2s by s square plus a square ds minus integral of 2s by s square plus b square ds, which is equal to 1 by 2 into integral of 2s by s square plus a square. Means here in the denominator the function is s square plus a square, and the derivative of this denominator function is in the numerator. Therefore, we have to write integral of this as logarithm of s square plus a square. Similarly, for this function also, this is logarithm of a square plus b square. 1 by 2 is common. The limits are s to infinity. That is equal to, now I am writing here, which is equal to 1 by 2 into, we have to use the result that log a minus log b is equal to logarithm of a by b. Therefore, we can write this as 1 by 2 into logarithm of s square plus a square divided by s square plus b square between the limits s and infinity. Which is equal to 1 by 2 into logarithm of, we take s square from the numerator in common. Therefore, in the numerator we can write s square into 1 plus a square by s square divided by, similarly take s square in the denominator, take a square outside in the denominator also, we get s square into 1 plus b square by s square between the limits s and infinity. This s square and s square cancelled, and we apply the limits. When we apply the upper limit infinity, we get this is equal to 1 by 2 into logarithm of 1 plus a square by infinity. A is a constant, therefore a square by infinity means this term will become 0. That means in the numerator we get 1. Similarly, in the denominator this will become 1. Therefore, when we apply the upper limit to infinity, we get log 1 minus log. When we apply s for s means these terms are the same. Therefore, we get log 1 by 2 into log 1 minus log 1 plus a square by a square divided by 1 plus b square by a square. That is equal to 1 by 2 into, here log 1 minus this can be written as On cross multiplication we get like this, a square plus a square by a square plus b square, which is equal to 1 by 2 into we can use once again the property log a minus log b is logarithm of a by b, means we can write 1 by 2 into logarithm of a by b, means this is a is 1 here, b is a square plus a square divided by a square plus b square. Therefore, we can write the reciprocal of this term, logarithm of a square plus b square divided by a square plus a square. This can be written as logarithm of a square plus b square divided by a square plus a square, the whole raised to 1 by 2, because m log a is logarithm of a raised to m. This is equal to logarithm of square root of a square plus b square divided by a square plus a square. This is the Laplace transform of cos a t minus cos b t all divided by t, that is logarithm of root a square plus b square divided by a square plus a square. If here instead of t it is t square, then we have to use this property once again. That means we have to integrate this function between the limits s and infinity once again. Then we will get the Laplace transform of cos a t minus cos b t divided by t square. If it is t cube, then once again we integrate between the limits s and infinity, and so on. Now we have to work out some example problems. Evaluate Laplace transform of e raised to minus t into integral from 0 to t sin t divided by t dt. That is, we have to multiply e raised to minus t by this integral and find the Laplace transform. Here, first of all, we have to find the Laplace transform of sin t. We know that Laplace transform of sin a t is a by a square plus a square, which is an elementary transform. Therefore, Laplace transform of sin t is equal to 1 by a square plus 1 square means 1. That is L of sin t equal to 1 by a square plus 1. Now, we want to find we have to find the Laplace transform of sin t divided by t, which is equal to integral from s to infinity 1 by a square plus 1 ds. Because we have the property Laplace transform of f of t by t is integral from s to infinity f of s ds, where f of s is the Laplace transform of the numerator function f of t. Here it is for sin t. Therefore, we can write L of sin t by t as integral from s to infinity 1 by s square plus 1 ds. This is equal to tan inverse s between the limits s and infinity, that is equal to tan inverse infinity minus tan inverse s, that is pi by 2 minus s, sorry, pi by 2 minus tan inverse s, that is cot inverse s. Laplace transform of sin t divided by t is cot inverse s by the property of division by t. Now, we want to find the Laplace transform of integral 0 to t sin t by t dt. we have the Laplace transform of function sin t by t, which is cot inverses. Therefore, by the property of transform of integrals, we can write this is equal to 1 by s into f of s, where f of s is taken as this cot inverse s, because Laplace transform of integral from 0 to t f of t dt is 1 by s into f of s, where f of s is the Laplace transform of this integrand f of t. Here it is sin t by t, and the Laplace transform of sin t by t is cot inverses, which is taken as f of s. Therefore, by this property of integration of transforms, we can write L of integral 0 to t sin t by t dt is equal to 1 by s into cot inverse s. Therefore, Laplace transform of e raised to minus t multiplied by integral from 0 to t sin t by t dt is equal to 1 by s plus 1 into cot inverse s plus 1. This is from the first shifting property of Laplace transform. The property is Laplace transform of a function multiplied by e raised to a t is f of s minus a, where f of s is the Laplace transform of this function f of t. Then the Laplace transform of this function multiplied by e raised to a t is f of s minus a, means we just replace s by s minus a. Therefore, here Laplace transform of this function, this integral, we have to take this integral as a function of t, and the corresponding Laplace transform is 1 by s into cot inverse s. Therefore, we multiply this function, means the corresponding Laplace transform is obtained by replacing s by s minus minus 1, that means replace s by s plus 1. Therefore, this is equal to 1 by s plus 1 cot inverse s plus 1, which is the required transform. In this problem, we used three properties. Consider this problem. Evaluate L of t into integral from 0 to t sin t by t e raised to minus t dt into e raised to minus t dt. We have to multiply this integral by t and then find the Laplace transform. First of all, we have to find the Laplace transform of sin t. L of sin t as 1 by s square plus 1. Then Laplace transform of sin t by t. Which is equal to, by the property of division by t, we can write the corresponding Laplace transform as integral from s to infinity f of s ds. Here f of s is taken as this ds, which is equal to tan inverse s between the limits s and infinity, that is equal to pi by 2 minus tan inverse s, that is cot inverse s. Now we want to find the Laplace transform of sin t by t multiplied by e raised to minus t, that is by the first shifting theorem we can write the Laplace transform as cot inverse s plus 1, because we multiply this function with e raised to minus t means we have to replace s by s plus 1 in the Laplace transform of sin t by t. Here Laplace transform of sin t by t is cot inverse s. Therefore, Laplace transform of sin t by t multiplied by e raised to minus t is cot inverse s plus 1. Now, we want to find the Laplace transform of integral from 0 to t sin t by t e raised to minus t dt. We use the property of transform of integrals. We can write this Laplace transform as 1 by s into cot inverse of s plus 1, because f of s is the Laplace transform of a function f of t. Then integral from the limit 0 to t f of t dt is obtained by multiplying f of s with 1 by s. Here f of s is taken as cot inverse s plus 1 and the corresponding function is sin t by t into e raised to minus t. Therefore, integral of this function means 1 by s into cot inverse s plus 1 in the corresponding Laplace transform. And finally, we want to find L of t into integral from 0 to t sin t by t e raised to minus t dt. That is, here we multiply this integral by t. Therefore, we can use the property of multiplication by t, which is equal to minus 1 raised to 1, that is minus 1 into first derivative of f of s with respect to s. Here f of s is taken as 1 by s into cot inverse s plus 1, d by ds of 1 by s into cot inverse s plus 1. Which is equal to on differentiation we get this as s plus s square plus 2s plus 2 into cot inverse s divided by, here s plus 1 divided by s square into s square plus 2s plus 2. On differentiation we get L of t into integral from 0 to t sin t by t e raised to t dt as s plus s square plus 2s plus 2 into cot inverse s plus 1 divided by s square into s square plus 2s plus 2. Now, we can evaluate the integrals of the form integral from 0 to infinity e raised to minus st f of t dt by using the properties of Laplace transform. Consider this problem. Evaluate the integral from 0 to infinity t into e raised to minus 3t into e raised to minus 3t into sin t dt. By the definition of Laplace transform, this is the definition of Laplace transform. This is L of f of t. Comparing with the definition of Laplace transform, we can write this as, this is equal to Laplace transform of, here take the function as t into sin tt, f of t as t into sin tt into e raised to minus 3t. This is of this form where s is taken as 3, f of t is taken as t into sin t. Therefore, this is equal to Laplace transform of t into sin t, where s is equal to 3. This is equal to, we have Laplace transform of sin t is equal to 1 by s square plus 1. Therefore, by the property of multiplication by t, L of t into sin t equal to minus 1 into d by ds of this function 1 by s square plus 1. This is from the property of Laplace transform, that is the multiplication by t, means we want to differentiate this function with respect to s and multiply by minus 1. That's equal to minus 1 into, in the denominator it is s square plus 1 square, here s square plus 1 into 0 minus 1 into 2s, that is equal to minus 2s. Minus 1 into minus 2s means 2s divided by s square plus 1 the whole square. Therefore, this is equal to, here we can write this as 2s divided by s square plus 1 the whole square, where s is 3. If we put s equal to 3 here in this function, we get 2 into 3 divided by 3 square plus 1 the whole square, that is 6 divided by 3 square is 9, 9 plus 1 is 10, 10 square means 100. This is the value of the given integral, that is we have to use the Laplace transform to integrate this type of integral. The limits are 0 and infinity, and the integrand is of the form e raised to minus st into f of t dt, in which case we can use the Laplace transform. Now let me conclude this session. In this session, we discussed some properties of the Laplace transform and evaluation of this type of integral using the Laplace transform. Thank you for listening this class. Have a nice day.